The Bode plot is kind of amazing. At its core, it's just a graph that shows the steady state frequency response of a linear time-invariant system. But what makes this special is that by looking at the Bode plot of an open loop system, we can actually make claims about how stable the closed loop system will be. And so that means that we can use it to design a closed loop system by adding poles, zeros, and gain to a controller that will shape the response of the open loop system. And typically what we're trying to do with a Bode plot is shape a response that has a certain amount of gain and phase margin. This is where we're looking at how close the phase is to minus 180 degrees when the magnitude is at 0 decibels, and then how close the magnitude is to 0 decibels when the phase is at minus 180 degrees. And here is where, if we don't have enough stability margin, we can augment the open loop system with a controller in such a way that provides us with the closed loop stability margins that we're looking for, which is pretty awesome when you think about it. But when I was first learning this, I kept running into questions that I didn't have direct answers for. Why do we only look at the steady state response? Why is frequency information alone enough to tell us about closed loop stability? And what do gain and phase margin actually mean? Not just how to read them off a plot, but why 0 decibels and minus 180 degrees? And so in this video, I'm going to try to answer those questions, and I think it'll be pretty interesting, so I hope you stick around for it. I'm Brian, and welcome to a MATLAB Tech Talk. For this first part, we're going to look at what steady state means and why is it important. Let's say that you have a stable linear time-invariant system and you apply a pure sine wave to it. What comes out? Well, after things settle down, what you get is another sine wave at the exact same frequency. It's just scaled in magnitude and shifted in phase. And we can see it, more clearly here if I plot the input and the output on the same graph. After the transient period, the output is scaled slightly smaller than the input, and then it's shifted almost completely out of phase. Now that's one of the fundamental properties of a linear time-invariant system. A sine wave in equals a sine wave out at the same frequency. But again, it's after things settle down. So why is there this initial transient period at the beginning? Well, here's the intuition behind it. If we zoom into the very beginning, the input starts at 0 and it's trending up in the input sine wave. Now the system is in some initial state, right? Maybe it's at rest, but it could be anything. But in this case, the output is also 0. So both the input and the output start at 0 for this particular example. But now let's move forward in time to where the steady state response is happening. At this point here, the input's in the same spot on the sine wave that we started at, right? It's at 0 and it's trending upwards. But look at where the output is. It's some negative value and it's trending down. And in fact, if you look at every point where the input is 0 and trending up, the output is always at the same steady state value. This is where the system wants to be at this point in the input sine wave. It wants to be negative and trending down. So we can see that at the beginning here, there's this mismatch between the starting condition and the state that the system wants to be in given this input. And the system can't jump instantly to it, so it has to catch up over time. And that catching up process is the transient response that we see here. Now, here's why this matters for the Bode plot. The Bode plot only shows you how a sinusoid is scaled and shifted for the steady state response. It doesn't take into account the transient response at the beginning. And that's because the steady state frequency response is what determines the long-term closed loop stability of a system. Once the transients die down and the system recovers from that initial mismatch, we can ask the question, is this long-term behavior, when it's placed in feedback, is it stable or not? Which brings us to the second question. Why is steady state frequency information enough to determine closed loop stability? Well, to answer that, let's close the loop around our open loop LTI system. So now the question is, if we input a signal into this system and it gets affected by the LTI system and then loops around again and again, will the response be stable or not? Now, it might be tough to imagine how any arbitrary input will behave in this system, but as we'll see later, it isn't hard to assess the stability for an individual sinusoid. And here is where Fourier comes in, because any signal can be described as a sum of sinusoids across a spectrum of frequencies. A step input, a ramp, or a random disturbance. We can think of all of these as a superposition of a bunch of sinusoids. And this is important for LTI systems because we know that in steady state, a sinusoid doesn't change frequency. So if we just look at the 10 Hz component of the signal going around the loop, it will always be 10 Hz in steady state. So this means that we can examine how each frequency passes through the system and around the loop on its own and ask, is this one frequency stable in feedback? Now, it doesn't matter if the input is a step or a ramp or any arbitrary function. If a 10 Hz signal is stable through the system in isolation, it will remain stable as part of the larger signal. So in this way, you can assess every individual frequency for stability, and then you've assessed every possible input. And that's why the Bode plot is sufficient for LTI systems. By looking at magnitude and phase shift for a particular frequency, you can make a claim as to whether that frequency will grow or shrink when it's placed in feedback. And then, with that logic, we can look across the entire spectrum and understand the entire stability picture. So, that brings us to the third question. How do we assess the stability for each frequency, and what do gain and phase margin actually mean? Now, to understand this, let's take a step back from the frequency domain and just think about stability in general. The defining characteristic of a stable LTI system is that all of the poles exist entirely in the left half of the S-plane. So as long as every closed loop pole is to the left of the j omega line, then it will be stable. Now let's take the open loop transfer function g of s. If we feed back the output, then the closed loop transfer function will be g of s over 1 plus g of s. So we can set the denominator to 0 to find the poles of this closed loop system. So 1 plus g of s must equal 0. But since g of s is just the open loop transfer function, we can write this as g of s equals minus 1. That means that for every value of s in our open loop system that meets this criteria, then that is where a pole will exist when we place that system in feedback. For example, if g of s equals 1 over s plus 1, then the open loop system has a stable pole at s equals minus 1. And if we place it in feedback, then the closed loop system will have a pole at 1 over s plus 1 equals minus 1, or s equals minus 2. So in this case, the closed loop system is stable, and we never had to look at a Bode plot, right? I mean, the pole is right here. All right, so why does all of this matter? Well, even though this system is stable, what we're trying to answer is how close is the pole from becoming unstable? You know, how close is it from crossing the j omega line and moving from the left half plane to the right half plane? And specifically in quantities that make physical sense, like how much gain will cause the pole to cross the line, or how much phase shift will do it. And here's how we can think about this. Since the j omega line is sort of the gatekeeper between stable and unstable poles, we can just look at that line and see if a closed loop pole falls on it. If it does, then we know that the closed loop system is on the verge of becoming unstable. So the way that we do this is that we take our closed loop transfer function, we look at the denominator to get the poles, right? And then we replace s with j omega to just look at the vertical line between the left and right planes. Now, if any point in g evaluated at j omega equals minus 1, then we know that there's a closed loop pole on the vertical line. And g evaluated at j omega is exactly what a Bode plot is showing us. If we take the magnitude of g of j omega, that gives us the magnitude Bode plot. And if we take the argument, or the angle of g of j omega, that gives us the phase Bode plot. And remember, we want to avoid g of j omega equals minus 1. So that means that when we're looking at a Bode plot, we just need to avoid whatever gain and phase are produced when this condition is met. Now, the magnitude of minus 1 is just 1, or it's 0 decibels if you're looking at it on a log scale like we do with Bode plots. So half of the problem is just to avoid this 0 decibels line. And then the argument of minus 1 is minus 180 degrees. It's also positive 180 degrees, but for many real systems, we're usually more concerned with the negative phase, since usually systems have delays and lag in the system that add that negative phase. So we want to avoid this minus 180 degree line. But -1 only occurs when 0 dB and minus 180 degrees happen simultaneously at the exact same frequency. Therefore, as we look at this Bode plot, if any frequencies along this whole spectrum produce 0 decibels and minus 180 degrees of phase, then we know that g of j omega equals -1. And so the closed loop system will then have a pole that is right on the verge of crossing over into instability, something that we probably want to avoid by adding in some margin. In other words, gain and phase margin each quantify the distance from that -1 point, but along different axes, along these more physically understandable quantities of gain and phase shift. All right, to end this, let's come back to those initial 3 questions. Why are we looking at steady state? Well, because the transients are caused by a mismatch in the initial conditions, and they reflect the initial conditions fading out over time, not the system's sustained response to an input. The forced sinusoidal response is what actually determines whether a particular frequency will be stable or not in the closed loop system once those transients are gone. Now, why is frequency information alone enough? Well, because in steady state, each frequency behaves independently around the loop. Assess each frequency, and because of what Fourier taught us, you've assessed every possible input. And then, what do the margins really mean? Well, they are a direct measure of how far the worst frequencies are from simultaneously hitting gain of 0 decibels and a phase of minus 180 degrees, which is the exact condition where a pole moves onto the j omega line. And that's what makes the Bode plot a powerful tool for designing closed-loop control systems, because now, when you add poles and zeros and gain in the form of a controller, you have something concrete to design to. When you're shaping the frequency response using a Bode plot, gain and phase margin become the targets for robustness in your design. All right, I hope this video helps you and you have a little more appreciation and intuition behind this amazing diagram. But if you do want to dive deeper into how Bode plots are used for system analysis and controller design, there's a link below to our full Tech Talk series. And if you want to expand beyond Bode plots, you can find all of the Tech Talk videos across many different topics, nicely organized at mathworks.com. Thanks for watching, and I'll see you next time.